Hello everyone. In this video we are going to discuss IKE or IKE as a short, and we'll see that how IKE works and how it helps us simplify the process of IPSec tunnel establishment or security association development between the two peers. As you can see on the slide, that IKE or IKE is a UDP based application layer protocol. It runs on top of UDP, so we can call it an application layer protocol, and it's based on a framework defined by ISAKMP, ISAKMP, or simply speaking ISAKMP. It's an abbreviation for Internet Security Association and Key Management Protocol. ISAKMP, Internet Security Association and Key Management Protocol. So this is the framework which governs the messages that are being exchanged between IKE peers. This protocol, IKE, implements automatic key negotiation and IPSec SA establishment. It helps us negotiate the keys between the two peers, and it helps us develop IPSec Security Association, which is responsible for providing secure communication between the two peers. We can work without IKE as well, with manual key exchange or with manual key definition and with manual configuration. However, if we have a large deployment, it's not a scalable solution. So using IKE is always easier, or it simplifies things in case of bigger deployments. So it simplifies IPSec usage and management, and it facilitates IPSec configuration and maintenance. So as I said, for smaller environments you can work without IKE, but for larger environments, larger setups, larger networks, IKE always is a better option. So if you look at the relationship between IKE and IPSec, IKE is responsible for, or we can say that IKE starts the task first. IKE takes the responsibility of initial negotiation between the two peers. There are two peers, peer A and peer B. First, IKE is going to develop an IKE security association between the two peers. There's going to be a negotiation where they are going to agree for how to exchange the key information with each other. That is the responsibility of IKE. IKE is going to establish an IKE SA or IKE security association and negotiate or develop an understanding between the two peers about how are we going to establish the IPSec Security Association. So first, the IKE Security Association is developed. Based on that security association or based on that SA, we are then going to establish an IPSec SA or IPSec Security Association. And this IPSec Security Association is going to make sure that the communication between the two sides is done securely, and nobody can intrude or nobody can sabotage or nobody can look into that communication. So first IKE performs its task, performs its role, and then IPSec is going to perform its role. And basically what both of them are doing is that both of them are developing security associations between the two peers. First we are going to have IKE Security Association, and then we are going to have IPSec Security Association. One other thing which you need to remember is that IKE Security Associations are bidirectional, whereas IPSec Security Associations are unidirectional, which means that you are going to have two one-way security associations in case of IPSec. So just ignore this bidirectional, because IPSec Security Associations are unidirectional, and you need to have two bidirectional associations in order to have a two-way communication, two-way secure communication between the two peers. So let's take a look at what an SA is, what a security association exactly is. We have been talking about security association a lot. So this slide explains what a security association is. So basically security association is kind of an understanding between the two peers, where the two peers define or agree upon a set of parameters for data transmission between the two peers. The parameters include security protocol, characteristics of data flows to be protected, which means that which protocol or which type of traffic is going to be protected, data encapsulation mode, data encryption algorithm, authentication algorithm, the key value or what key is going to be used, and the security association lifetime. For how long is the security association going to be used before we exchange or before we agree upon a new security association, just to keep the communication constantly secure. So an SA is uniquely defined by a triplet including SPI, Security Parameters Index. We saw this in the header of the IPSec protocols, either AH or ESP. Then the destination IP address and the security protocol ID. So these three parameters or these three values uniquely identify any security association. A security association is unidirectional. As I mentioned that for IPSec, security association is unidirectional. So security associations are required in both the incoming and outgoing directions. An IPSA can be established in manual or in IKE auto negotiation mode. If you are doing it manual, there's a lot of overhead. You need to do a lot of configuration. So for smaller environments, this can be done. However, if it's a large network, if it's a large multiple peers or a large number of devices, then it is always recommended that you use IKE auto negotiation because it simplifies and makes our life easier. So if you look at the different components of IKE or different functionalities which the IKE provides us or performs, so we see that IKE provides us with identity authentication, identity protection, Diffie-Hellman key exchange algorithm or simply DH key exchange algorithm, and finally PFS or perfect forward secrecy. These are the different tasks which IKE provides in order to make the communication secure and in order to ensure that IPSec is able to perform its tasks later on. So first IKE is going to perform these tasks and then it is going to hand over the proceedings or hand over the operation to IPSec to make the communication secure. So let's take a look at these tasks one by one. First of all, we are going to look at the identity authentication and see what identity authentication is and what it does. So the identity authentication makes sure or it authenticates the identity of the two peers. We can use either the IP address to identify the peer on the other side, or we can use a name to identify the peer on the other side. When do we use the IP address and when do we use the name? We'll look at it later on. However, for now, you should remember that we can use either one of them, either the IP address or the name of the peer. And identity authentication using either the IP address or the name can be achieved using any of these mechanisms or modes. We can either use a pre-shared key for authentication, or we can have an RSS signature authentication, or we can have a digital envelope authentication. Pre-shared key authentication means that there is a pre-shared key which is defined on both sides, and that is going to be used for authenticating the two sides to each other. RSS signature means that we are using a certification authority or a CA for authentication, and digital envelope authentication means that we are going to encrypt the traffic which is going to be exchanged between the two sides, or we can say that we can generate a random symmetric key, and that random symmetric key is going to be used for securing the key exchange between the two sides. So you can use either one of these mechanisms for authenticating the identity of the two peers between each other, and we call this identity authentication. The next one is the IKE security mechanism that we are going to discuss is the identity protection. In identity protection, we make sure that once the peers have been authenticated, then their identity is protected and nobody can, in the middle, nobody can look at whatever is being exchanged between them or the keys that are being exchanged between them, which means that we need to make sure that the traffic or the key exchange between them is encrypted. So this encryption can be done using either of these algorithms. You can either use DES or 3DES or AES with 128-bit encryption, 182-bit encryption, or 256-bit encryption, or we can use SM1 or SM4. The most common these days, the most common algorithm that we use for identity protection is AES 256, either AES 128 or AES 256. As you can understand, obviously AES 256 is more secure than AES 128. However, it puts more load on the device, so it's your choice whether to use AES 124 or AES 128 or AES 256, but generally AES 256 is more secure. Then next comes the DH key exchange algorithm, that how are the keys securely exchanged between the devices. Now we have authenticated the devices and we have agreed upon the algorithm which is going to be used for exchanging the keys securely, for secure communication between the two devices. How is it actually going to be exchanged, how the traffic is going to be exchanged between them. So that's governed by the Diffie-Hellman key exchange algorithm or DH key algorithm, now that we have agreed upon the parameters in the previous slides. So the initiator and the responder, or the two peers, exchange their key materials through key exchange and nonce payload in ISACamp messages. As you know, that ISACamp is the framework which is responsible for supporting, or which is responsible for making IKE possible. So Diffie-Hellman uses ISACamp messages to exchange the key materials, and these key materials include two things: key exchange payload and the nonce payload. What is key exchange? Key exchange is used to exchange the public DH values, or Diffie-Hellman values, which are open to anybody. Generally it's a PKI, public key infrastructure, and nonce is the random number or the temporary random number that is used for generating the hash values or for encrypting the traffic which is used. Don't delve too much into exactly what key exchange and nonce is. Just remember that these are the two materials which are used, or these are the two payloads which are used for making the communication secure between the two peers. In the DH algorithm, two IKE peers exchange only their key materials and do not exchange the real shared key. This is important. This is extremely important to understand, that at no time do we exchange the actual keys between the two peers, because if we exchange the actual keys, somebody sitting in the middle can pick up that communication and can actually know the key, and therefore they can decrypt the traffic that is going to be exchanged eventually between the two peers. Therefore, even though hackers intercept the DH values and temporary numbers, they cannot calculate the shared key. So since the keys are not being exchanged directly between the two peers, so even if somebody picks up the communication, they cannot decipher or they cannot understand the key, at least not easily. This is the essence of DH algorithm. This is just showing the different payloads, the key exchange and the nonce payload between the two peers. So this is kind of exchanging. This explains the DH key exchange mechanism a little bit in more detail. Either we can have a pre-shared key, or we can use the digital envelope or RSA mechanism for exchanging the keys. So either we can have a pre-shared key, or we can use a shared key which is going to be shared between the two using the Diffie-Hellman algorithm or DH algorithm. In addition to this shared key, we are also going to have the pseudo-random function or the nonce functionality. So either one of them is going to be used for generating a shared key, which when combined with the S key ID or shared key ID, they are going to generate three random keys: S key ID A, S key ID E, and S key ID B. S key ID A is generally used for authentication, E is used for encryption, and D is used for deriving the next keys. So these keys are exchanged with the other side, and the other side, using these keys, receive these keys. And since the values are not exchanged directly, they can decipher the keys, only they can decrypt the information, and then these two sides are going to reach the same conclusion, and they are going to reach or develop an understanding with the same shared key value. And those values, or these keys which have been exchanged, these are going to be used for further communication between the two sides. And since these keys have been agreed upon between these two peers, therefore the communication is going to be secure from now onwards. And finally, we have perfect forward secrecy, or PFS. PFS means that if, for example, in the absence of PFS, if we do not have PFS, then this means that if one key has been generated and we generate the subsequent keys based on this original key, then if somebody decrypts or somebody can decipher this original key or the root key, all the remaining keys which have been derived from this root key will also be deciphered or decrypted. So this means that our entire security mechanism has been compromised. So it is very important to make sure that the key which is used initially is not used for generating the subsequent keys, because in this case, this is what we call the perfect forward secrecy. So in this case, if one of the keys is decrypted as well, since the remaining or the next keys are not based on that original key, therefore the remaining keys will not be compromised, and the hacker cannot actually decipher or decrypt the entire communication even if one of the keys has been compromised. So we call this perfect forward secrecy, and this is up to us. This is an optional thing, whether we want to use PFS or we want to secure the communication without using PFS. So these were some of the mechanisms which IKE uses, and we have developed an understanding of how IKE exchanges the keys between the two peers. In the next video, we are going to look at the different versions of IKE and the different modes that IKE uses in those versions. And so we'll take a detailed look at certain other features of IKE in the next video. So see you in the next video. Thank you.